All right. Hi, everybody. My name is Ian Steiner. I am a senior principal engineer at Intel and one of the chief architects of Cascade Lake, or the second-gen Intel Xeon Scalable processor. I'm really bad with code names, so we'll see how many times I get them right. So before I actually dive into a bunch of the technical stuff of kind of what we built with Cascade Lake, I kind of want to reflect a little bit on kind of where we've actually come in the last few years. The first processor that sort of I spent a lot of my time on was a processor that, well, I called Jaketown. The outside world had the code name of Sandy Bridge, and then the marketing guys had the Xeon E5 2600 processor. So I spent like, I don't know, maybe 5 years of my early career on this processor. And so it's kind of near and dear to my heart. And we've actually seen a lot of things change in this time, and I think it's kind of exciting to see how things have changed over the last 7 years since we launched that processor. Back then, it was kind of like almost the early days of the cloud. Some of these big customers and hyperscalers were around, but we hadn't seen really the move to the cloud that's really happened in the last 7 years. And sort of what we've been doing in this time is really taking time to build a lot of good engineering relationships with these companies and kind of grow up with them as the cloud kind of develops and learn about what their real pain points are. And so a lot of the things that we're trying to do here today with this processor is really think about what some of those unique pain points are and try to bring solutions to the customers for their unique pain points that might not show up in traditional benchmarks. Another interesting thing that I've sort of seen is back then, there was a lot of talk of in the data center and enterprise, a lot of people had really low utilizations. And so what do we do about low utilization? Back then, we'd talk about spec power and how do I save energy. I personally spent about 5 years doing power management, optimization. But what we've heard from a lot of our customers is, saving energy is nice, but what we'd really like to do is use our processors more effectively. So how do we drive up that utilization? Rather than trying to save energy, let's actually get from 30% to 50% to 70% utilized typically, and just make a better use of our investment. And so that's one of the things we're really trying to focus on today, and as we look to the future, is how do we really help our customers really capitalize on their investments? Back then, we introduced our first AVX versions. I guess we called it AVX 1, maybe. But it was mostly all about HPC. So we had some nice cool proof points with the big HPC workloads. And what we've seen since that time is a lot of that heavy compute has sort of transitioned out of that HPC market into a lot of general purpose compute through AI and analytics. And so what's kind of cool is we've been building this foundation of wide vector compute within our cores, as well as throughout the memory subsystem to kind of feed the cores in order to enable that compute. And we've been doing that through HPC for years, and now we're able to take a lot of those foundations and apply them to artificial intelligence. The last one I wanted to mention is back then we had our first custom CPU for one of our big customers. I remember actually sitting in the lab, running some benchmarks, trying to tweak how we would make the thing look with them and talking to those guys on the phone. It was a lot of fun. And we've sort of taken that first thing and really scaled it out here. So now not only do we have dozens of customer customized CPUs, but we're also doing things where we're looking at specific usage models and workloads and trying to customize CPUs there. So that's kind of where we've come. And we're going to talk through next sort of what are the things that we're actually doing about all this stuff.
Can I ask you?
Yeah, please.
When you talk about customer asking for optimizations or whatever, are you talking now about large cloud providers first and then the others? Because it's, probably now they are the major consumers of this new kind of technology, and this could somehow put the traditional enterprises in second place.
Yeah, I mean, so the way that we kind of do this is not everyone can talk to everyone, right? I can't go talk to 50 different customers. It's not sustainable. But so what we do is we have engineers that will focus on, I think we call them the Super 7 cloud, the Next Wave cloud, people that focus on enterprise. And we try to really build close engagements with a lot of those different types of business so that we can really understand what their big pain points are or their big places that they want to see growth and try to build solutions to really help them out. So like me personally, I work a lot with some of our big cloud customers, but we've got other people that are looking at a lot of the next wave customers, whole teams that are really focused on enabling that business. We've got whole teams focused on the enterprise, networking, edge. So we're trying to sort of spread the love so we can really build that entire market.
And just this, there is a second question about the fact that, yes, the product lineup is really, really broad now. Now you have, in the same family, several processors, several SKUs, or whatever. But how do you, I don't know, find the balance between, the enterprise and because it's impossible to build a one-size-fits-all. No, even if you are putting different frequencies or different things, not all the customers are interested in AI. Not all the customers are interested. So you are putting a lot of features in these CPUs, but, and it increases the cost, but actually not everybody uses them.
Yeah, well, I think the way that we try to do this is like when we actually design our CPUs, we look and say, what is the area cost or the power cost of these different features, and how does that look for the broader market? A lot of the foundational stuff that takes up the bulk of the area, the power is really shared by everyone. And then what we can do is if, for example, there's a customer and they're just running old scalar code and they don't have any vectors, we can take those blocks and we can either clock gate them or power gate them depending on what we think is best on a given generation, so that they're not actually paying a penalty for that or a cost for that. And so but it's a balancing act to figure out how much stuff do you put into the CPU. But one thing I think that we do see is AI is really exploding, especially in inference on CPUs. And so the investments that we think are making there, it's not a niche like, I guess HPC is not really a niche, but it's not like a contained market. This is something that's really growing everywhere. So we think that there's really a lot of broad viability there.
Yeah, so the DL Boost had a couple of interesting benchmarks, but they're all talked about int8. Is that your implementation of a small floating point?
Yeah, so I'm going to get to that. So I'll take you guys all through int8, what it is, why we do it, some of the early perf data, so like some micro-benchmarking data, and then in another video or another talk, Niv's going to talk about some real-world benchmarks and how they work. So I'm a CPU architect, so I'm going to do some micro-benchmarking kind of fun stuff, and then she'll talk about the real workloads.
I guess my other question, you tend to focus on inferencing rather than training. Is there a particular reason?
Yeah. So the instruction, the DL Boost VNNI instruction that we have in this processor is an inference-optimized instruction. And we'll go through why that all is. We're committed to doing training as well in the CPU. We've talked about...
in the CPU?
Yeah, so we've talked about, what's it called? bfloat 16, a new sort of data type that can be used for training and sometimes for inference. And that'll be coming in some future generations. And so on this particular generation, there's a lot of inference optimization, and so that's why we're focused on it. But we believe that inference and training, they can happen within the CPU, they can happen in FPGAs, accelerators. Like, we don't think there's a one-size-fits-all solution, and we're trying to make all of them work as well as we can. Okay. All right, I'm going to keep going otherwise I'm going to run out of time. Okay, so we'll do this one this quick. My agenda. So we're going to talk high-level stuff about the CPU, sort of the speeds and feeds real quick, how it's different from the prior generation. We'll talk about the new MCP processor that we have with up to 56 cores per socket. We'll go through DL Boost and VNNI, what those are and sort of how they work within the microarchitecture. I'm going to do a little teaser on data center persistent memory. We'll have another video on that later with Mohammed and Lily, and they'll really dive into details on those two. So I'm gonna go through that one pretty quick. Talk about some of the sort of workload optimized things that we're doing within our CPU based on the feedback and learnings we've been getting from sort of that growing up with the cloud customers and really learning about their pain points and growing up with the network stack and seeing what they're doing. And then finally, we'll touch a little bit on the mitigations that we have for security. Okay, so this slide's a little bit busy, but this is sort of the big spec sheet. The parts that are grayed out are kind of the things that haven't changed from the prior gen. It's a little bit hard to see on this screen. I apologize. The purple stuff that you can probably read are the big changes that we have here. So we'll talk about this new 9200 series next. We bumped the memory frequency up to 2933. We support some bigger DDR devices with up to 16 gigabit devices. Data center persistent memory we'll talk more about later. VNNI we'll talk more about, and then the security mitigations. The last one that I'm going to quickly touch on here is we continue to try to improve the process and the manufacturing capabilities that we have. And so, as we're able to learn more and improve what we're doing on 14 nanometer, we're trying to take that and give it back to the customers. And so, sort of across the stack, there's really a range of performance boosts that you'll see. If you look at the top of the stack, they're modest. Some of the middle of the stack actually has some pretty substantial gains. We actually have a lot of volume in those middle SKUs, and so some of our customers can actually get some pretty nice performance benefits. And I believe the pricing is the same, but I'm not a pricing person, so I don't know for sure. Any questions on this one?
So what's the process level for the new scalable processors? Is that 10 nanometers? Or?
These are all 14 nanometer processors.
They're 14 nanometers. So the FPGA is 10?
The FPGA that we announced today is 10. So the first thing we've done sort of at a high level is we have a new kind of class of processors that we're introducing for the first time with this generation. In sort of the past, and as well as what we're doing on a large portion of our stack in Cascade Lake, is sort of our traditional two-socket system. So in the way this picture kind of works is we've got these dark blue dies, and they're, in this example here, I'm using 28-core examples. And then they're inside of a package. We've got 6 channels of DDR, 2 or 3 UPI links connecting them. And this is sort of like the workhorse. So these two-socket servers are really the bread and butter of what we build. But we were getting some feedback that some customers really cared about how do we get really dense compute in our data center. And so in particular in the HPC space, they were interested in, I've got these racks and they've got a ton of power delivery capability and I've got really awesome cooling. How can I take these things? And I really want to get as much compute as possible into as small of an area as possible. So that's sort of where we introduced these 9200 series processors. And so what they do is we take 2 of these same dies, we stick them together into a BGA, and it's kind of like you have a two-socket system in sort of the form factor of a traditional two-socket system. And within that, it's actually kind of like what would have previously been a 4-socket system. So we've got a fully connected topology using UPI across all of the CPU dies. And this allows us to get really high performance for some of these HPC workloads and HPC users that really demand high density. To do this, we crank up the TDP up to 250 to 400 watts. So that's not for everyone, but again, there's a sort of a portion of our customer base that really is okay with doing some pretty radical things with cooling technologies.
So when we look at this diagram, we're looking at, if it's a dual socket system, we're looking at 4 28-core dies, not 2 56-core dies.
That's correct.
Okay.
That's correct. So then they have, there would be 4 NUMA domains for the software that the software sees. That works great in some of the HPC spaces where they're able to do NUMA optimizations already and leverage MPI and whatnot to manage all of their data movement.
Doesn't it create a little bit of complexity in the backend to manage, all the access that you have to do on the lanes that are managed from, the one of the other processor? Meaning the first one is really simple configuration. We always seen that, and the second one is more similar to the old 4-socket design.
Right.
That was always slower at the end.
So it depends on the workload. Like if you pick just any old random workload off of, and try to run it on a 4-socket box, they don't always get perfect scaling when we go from 2 sockets to 4 sockets. But one of the things that we see is there are a class of HPC workloads where they already have those optimizations that enable good scaling. And so because a lot of those class of workloads already have that sort of inherent to them, it sort of works naturally. But like, if I took a traditional smaller database or something, and I took Cassandra and tried to run it on this thing, it might not scale, with 2x performance like you would see in some of the HPC workloads.
I see.
And that's why we don't think like one's better than the other. It really depends on, what are your workloads, what are your constraints, are you okay trying to cool 400 watts? And what we've heard is that there's just this wide range of customers. We have people that want to build 70-watt things in really tight, thermally constrained environments. And we have people come into us and are like, 400, why not 5? We can try big stuff. So we're really trying to see how we can take these CPUs and make them cover as broad a space as possible.
And what's the performance improvement per core?
So it depends on the workload. So for a lot, and it depends on the SKU, and it varies a lot. We don't have a lot of big IPC improvements on this generation. The biggest change is the addition of the VNNI instruction, which we'll talk about, I think, next. So I'm going to go there now. OK, so before I talk about VNNI, you guys are asking about int8 and what it is. So this is my opportunity to try to actually explain what we're talking about with VNNI and int8. And so when we look at deep learning, and actually a lot of HPC, one of the fundamental operations that a lot of the algorithms do is matrix multiplies. And so what is a matrix multiply? You have one matrix here, you have another matrix here, and you're sort of taking a row from one, a column from another, doing multiplies and accumulating them with a dot product into a single value. So it's just a ton of repetitive multiplies, and then accumulation of a value into a single element in the destination array. And so we've been doing this in HPC as well as in AI training for a long time using floating point. And so it works great there. It's got this massive dynamic range, so you can have big values, small values. It has pretty amazing levels of accuracy as well. But what we've seen is that for inference, we can actually sort of compress that down to int8 and still get the job done with good accuracy. So why would we do that? The simplest way to think about it is floating point uses 32 bits per operation. int8 uses only 8 bits. So I can do 4 times as many operations with a single vector instruction. My multiplies are actually smaller, and smaller multiplies are easier. You can imagine back in school when you were doing multiplies by hand. Would you want to multiply 8 one-digit numbers, or would you want to multiply 2 8-digit numbers? Like, we can all do single-digit multiplies in our heads relatively quickly. Doing a big 8-digit multiply is hard. When you build it with Wallace chains in the CPU, it's the same idea. So those big multiplies are actually expensive from a power perspective. And so by moving down to int8, we can do things. We can do more dense compute. We can also take better advantage of our cache hierarchy because sort of the data sets that we're working on are smaller. And so that can put less stress on the memory subsystem. And we'll walk through some examples of how that all actually looks. Does that sort of answer your question from before on int8?
Yeah.
Yep. OK, so what does this kind of look like over the years? So across here on the bottom is some of the different types of ISA that we've developed from SSE3 all the way out to AVX512 and then AVX512 with VNNI. This top graph is sort of the scaling that we see across that ISA on a per clock basis for double precision and single precision floating point. And the purple graph is what we have for integers. And you can see it's sort of like lagging behind. And basically, we've really been focused a lot on floating point because that's what HPC wanted. That's what some of the early training wanted. And now that we've seen this move to try to use int8 for inference, we said, OK, it's time to actually try to build the same sort of optimizations into the integer space as well. And that's what we're doing with VNNI, where we sort of bring int8 to catch up with the sort of the foundations that we've already put in for double precision and single.
Could you go back to the prior slide just for a second?
Sure.
I'm sorry.
No problem.
One of the advantages of floating point is the vast range of values that one can actually create with FP32. An integer 8 is like 0 to 256 or 128 to minus 128. Is that going to be sufficient for AI inferencing?
Yeah, and so you have to do this quantization step to try to take the FP32
It's almost like CDs or something like that versus analog.
Yeah, and so a lot of the work that Niv and her team have been doing is to try to figure out how we take those models that are in floating point today, move them into the integer space through that quantization step, not lose any accuracy, and then get the performance. And so there's like an extra step in the middle where at least today humans are a little bit involved to make that transition. But you get this big performance gain by taking the work.
And most of the frameworks and all that are all FP-based frameworks, TensorFlow and things of that nature. So you're supporting software frameworks to implement this?
And we'll talk about that on the next slide.
Okay.
The world can't hear you, Niv. Maybe we can get you a mic and then you can talk.
Okay.
Okay, but today, is there a difference in the accuracy?
Yeah, and so the accuracy difference is very small. So for a lot of things, we've got less than 0.5% accuracy decrease, and then for some, it's even smaller than that. Niv will actually show, like for a bunch of different workloads, some of those specific values.
I just want to add to what Ian was saying. When you...
Oh, just real quick, this is Andres. He's one of our AI experts in our cloud group at Intel.
When you look at the distribution of values in what you call a tensor or high-dimensional array, which are the data inputs that go into the neural networks or the data format of, or the way you represent the weights in a model, the distribution tends to be small, so that you can often represent all the values in a tensor with just 8 bits and one common exponent or one common multiplier. So what we're doing is we find what is the common multiplier. When we need additional granularity, we can actually subdivide the tensor into smaller subtensors. And we actually, for example, we can break it by the number of channels, which is one of the ways that the data is organized in these deep learning models. And we can have one factor for each different channel. So we find that 8-bit is sufficient for many different workloads. Now, there might be some that it won't be, but for many, it is. And just one more point. So there is already support in the frameworks for int8, and it's been going on for a while. If you look at TensorFlow, which is the most popular framework in the deep learning community, TensorFlow has support for int8 in particular, because even before Intel, before we added 8-bit support to our hardware, Google had developed their own hardware with 8-bit support, which is for their inference workload. So they actually were one of the leads to show, hey, int8 is possible. We have hardware and software to support it. And by Intel adding int8 native support to our CPUs, we will provide the broad ecosystem to take advantage of this additional performance boost.
Okay, thanks, Andres. Okay, so what is DL Boost in VNNI? So first off, when we actually did these multiply accumulates, this foundation of doing matrix multiplies on the prior generation on Skylake or Skylake, what we would do is it actually took 3 separate instructions in order to perform that multiply accumulate. First, we would actually do the 8-bit multiply into an int8, into an int16. We would then have to upconvert it into int32, and then we would do the accumulation step. And so this whole operation, in order to take those 2 vectors of int8 numbers and then perform the matrix multiply into an int32 accumulator, would take 3 instructions. Now we have 2 ports that can do this at a time inside of the core, and so we could sort of do 2 of these in parallel within the prior generation. And so then what we have with DL Boost with VNNI on Cascade Lake or the 2nd gen processor is we have all of this in a single instruction. And so every cycle then we can take, or potentially with every cycle we can take 2 vectors of 8-bit integers, we can do that multiply and then accumulate, and we can do 2 of those at a time. And that's where we sort of get this big 3x potential improvement just with int8 computes and max per cycle. Now, it's not all just what the peak compute is. It's really about using it. And so we're going to talk a little bit next about what do we actually see with different types of matrices and whatnot. And then later, we'll talk about some real workloads and how they're actually seeing the performance.
You said there's a human step involved right now, right?
Yeah, so this is when we want to go from a trained model that's been trained in something like FP32, and then we want to go and quantize that into the integer space to do the actual inference. And that's today a place where there's some work that needs to be done on a given model.
Okay.
Okay. Okay, so what does this kind of look like then? So if we compare floating point 32 to int8 with DL boost, we can get up to 4x boost in those multiply accumulates per cycle. What we'll see on the next slide is you can roughly get something like about 4x improvement in performance per watt if you sort of look at the power of the CPU. We get decreased memory bandwidth, and we can get sort of improved cache performance because we're working with smaller data sets. And we'll kind of walk through some micro benchmarks next showing each of these. Sort of the way software works is we have workloads that are sort of calling in and doing these inference jobs, and those workloads are making use of these topologies that implement these different machine learning models. Those are then implemented on top of the variety of different frameworks that are out there. And what we've been doing is sort of doing optimization between these frameworks and this set of libraries that we have called MKL-DNN. These are some open source libraries that are sort of optimized with primitives that do the necessary steps for deep learning that have been optimized for our processors. And so there's been a lot of work in co-optimization across the frameworks into how they actually use the libraries for the kernels within the libraries, and then working with guys like me in the hardware side that actually understand what's going on in the hardware so we can really get good co-optimization across all of these steps. So we've been working hard to really get this all done before launch so that we can open source it all and bring it to market so that it's available for people to just use. Okay. So next up, we're going to talk about some of the micro benchmarks. I'm going to geek out a little bit. So bunch of data here. What we've done here is those topologies that we talked about that were implemented on top of the frameworks, they make a bunch of library calls into MKL-DNN. So if I look across a bunch of different topologies, I can actually say, well, what are the API calls that they're making? What are they doing with our libraries? And then we can just micro benchmark them. So each of these are sort of some of the different workloads that we have sort of micro benchmarks for within MKL-DNN that people could go run today. And then what we do is we just run some of those individual API calls over and over again, and we can see what their performance looks like. So each of the different data points in these graphs represent a different API call that would exist in these different workloads. And so up on top, we just have performance. And so we've got FP32, we've got int8 from the prior generation if you did it with just regular old AVX512, and then the top is the purple with DL boost and VNNI. And so you can see there's a range of different types of performance that you can get depending on the API call you're making. If you've got a big giant matrix and you're multiplying it with another big giant square matrix, you can get really awesome throughput. Not everything's pretty like that in the real world. And so sometimes you see things like over here where the actual efficiency that you're getting doing these matrix multiplies, you can imagine a couple of long, skinny, or tall matrices that you're multiplying together. Their efficiencies might not be quite as high. And so what we wanted to do here is kind of capture the full gamut of cases that have really good performance, as well as some of the cases that are they're bound by other things within the system. And what you can see is for all these different types of scenarios, we can get some pretty significant performance gains using the new capabilities.
What's the bottom charts there?
The bottom chart's next. So hold on a second. So first up, the performance. And so you can see VNNI, with FP32. A modest boost when we go to int8 on the prior gen, but then when we go to VNNI, you can get the nice 4x boost in some of these cases. Now on the bottom, we're going to show power numbers. And so for all these studies, what I've done is I've locked the frequency just so that I can go and try to understand what the characteristics look like in the system. So I'm locking my frequency, and then I run these different workloads with the different data types or the different instruction sets. On the same CPU, these are all on a single CPU. And then look at the power numbers. And so the dark blue, again, is floating point. When we go to VNNI, we see a nice power drop. It's more efficient, but again, we're not getting a huge performance gain. But then when we go to when we go to int8, we don't get a huge performance gain. When we go to VNNI, you can see the power comes back up, and it's roughly the same as what we would have seen with floating point 32. So despite the fact that we sort of get these big 4x improvements in performance, we're doing it at roughly the same power. That's really one of the fundamental things that we're trying to achieve here is how do we get the most compute done with some constrained amount of power. And so we think we've done a really good job of bringing that really efficient performance per watt to the system. Okay. All right, so next up, we're going to look at memory bandwidth. So same kind of graphs. This time I took out just the regular int8, and I'm just showing FP32 and VNNI. And so again, these are a bunch of different API calls that we're making into MKL. And what we do is we show the memory bandwidth that those different API calls make. And so there's some things that live within our caches, and they don't really use the memory subsystem a whole lot. We have other APIs, like we see here, where the memory bandwidth is really high. And so in that case, those would be somewhat memory-bound workloads. And so some of the additional compute might not help. But because we've been able to shrink down to int8 and get those smaller data types, we actually are more effectively making use of our cache hierarchy. So we can really bring bring the bandwidth down and really keep our operation coming out of our caches and keep the core compute fed. This is something that we kind of tried to build in advance. And so if you remember from the prior generation, we kind of changed around our cache hierarchy and really bumped up the size of our L2 caches. One of the reasons we've done that is we're trying to really get as much capacity as close as we can to the compute so that we can hold these data sets within the cores and then get as much performance out of them as possible. Okay?
I'm just question is, why wouldn't it be, a factor of 4 better for across the board? Because you have to load cache occasionally, or
Yeah, exactly. You're not out, like these workloads aren't just simple gems with big matrices. They're doing real stuff, and sometimes you're just doing something else. And if you're not doing a VNNI, if you're going to load some memory or something, or doing some other compute that's not, a matrix multiply, then that sort of reduces the amount of performance that you get. And again, these are all micro benchmarks, which are nice for kind of stress testing the hardware. What really matters is what the real workloads look like across a range of different types of topologies, and that's what Niv will talk about later. Okay, I'm going to keep rolling because I'm a little behind. So I'm going to do this slide real fast. So switch gears a little bit to Intel Optane DC persistent memory. So obviously, this is one of the biggest things that we've done in our CPU and within our company, for the server side at least, in a long time. It's pretty exciting to kind of look at how we can go to a new cache hierarchy, a new memory hierarchy. I'm going to quickly go through this slide. What we've done in Optane DC persistent memory is we actually have 2 modes of operation that we try to use. So the first mode is what we call memory mode. And in this mode, the memory sort of, or the DDR sort of operates as a cache for the memory in DC persistent memory. And so sort of the workload or the user sort of sees this big physical address space that sort of is mapped by all of that persistent memory that's out there. Or sorry, in this case, it's not persistent, it's volatile. It's sort of the full address space of the DCP mem. And then the DDR in the system operates as a cache, so that when the user goes and wants to make use of a given piece of data, we try to keep as much of it as we can in that DRAM cache so that they can get really low latency and high bandwidth. And the main goal here is to sort of support legacy workloads where they can just sort of drop into a regular system and they don't have to know or care about any of this stuff. Now, the next thing that we do is what we call AppDirect mode. This is our persistent usage model where we actually have sort of a region of the address space that's mapped to the new persistent memory, and then a region of the address space that is mapped to traditional DDR. And then the workloads can be optimized to make use of this. And so in this case, the workloads have to know about this capability and then try to go take advantage of it. One of the things that we see is sort of across the space here is a lot of real world workloads don't actually work directly with data. And so they sort of will call into other layers of the system to kind of interact with that data. So they'll call into KV databases and such and try to get access to these big data stores that they care about. And so what we've been doing is saying, all right, what are the places, how do people really interact with big data? How do we go target those workloads, optimize them for AppDirect, so that they can sort of provide this foundational layer that all the other workloads in the system can just take advantage of. And so that's sort of our high-level strategy for one of the main areas that we're trying to use AppDirect. But kind of personally for me, that's kind of what we've been doing, but we have customers that are doing other stuff that we didn't think about. And the cool part to me is we're kind of creating a new opportunity, and there's a lot of smart people out there, and they're learning how to use this stuff, and they're already doing stuff that we didn't plan on. And so we're learning from them and try to figure out, okay, they're doing this thing. Maybe I can change my hardware in the future to really make that work even better. And that's the kind of thing that we're working on now.
So how do you decide how to set up the DIMM?
It's a boot time decision based on the type of workload you're running.
Okay.
So if you have a workload that you're running that is something that's been optimized for persistent memory and has those changes, you would do app direct. And again, we'll talk a little bit more about this one later. In the interest of time, I'm going to keep going, because I'm a little bit behind on schedule. OK, so again, I'm going to switch gears. Next, we're going to talk about some of the types of things that we put into the CPU to really help our customers sort of with their operational needs. One of the things that we've been seeing in the cloud as well as in the networking space is that there's a couple of sort of emerging usage models that our customers care about that don't really show up in a lot of traditional benchmarks. And so the first one that we've been seeing is this idea of isolated and consistent performance. And so you can imagine you're a user, you're going into one of our big public cloud service providers, and you're renting a little virtual machine with 4 cores. And then everybody else in this room was renting their own little virtual machine with 4 cores, and one of you guys is doing something horrible that's just consuming all of the cache or consuming all the memory bandwidth. That could really hurt the performance of the other users of that system. And so what we're trying to build here is capabilities that allow the people to really segment off the performance of those different users so that they get a more consistent experience. The next usage model is this idea of trying to increase utilization through prioritization. So kind of like I said earlier, before we had low utilized systems and people wanted to save power. Now what really we're saying is, OK, well, power saving is nice. How about we drive up the utilization instead, or in addition to the power savings that we already have? And so what we do there is we can identify really important work that really must have really good latency SLA. You're doing a query into a search engine. You want your answer in less than a millisecond. Or even more importantly, they want to deliver an ad to you in less than a millisecond. So it's bad if that thing gets delayed. But at the same time, maybe that guy uses 30, 50% of the utilization at a typical point in time. They've got tons of other things to do in their data center beyond just those search queries. And so what we're doing is we're trying to fill up those spare cycles with just all the other stuff that they've got to do. And so that's sort of this low priority work here. And so what we do is this low priority work, that could impact the performance of this latency sensitive work. And that just breaks the whole thing down, right? If you start to not be able to deliver ads in time, someone's going to get upset. The finance guys are going to be sad. And so what we're building here with RDT are capabilities that allow us to kind of control how those things interact with each other within the system. So we've had L3 capabilities before. And so the way we kind of do this is we look to do both monitoring and control of our system. So it's not good enough to just try to be able to figure out sort of what goes where, but you also want to be able to see how the system is actually behaving. So we started this with L3 monitoring and controls in prior generations. And then what we have today on the latest generation with Cascade Lake is control and monitoring for DDR bandwidth. And I'll show an example next of sort of how that can actually show good performance on some real workloads. OK, so what we have here is we start with a web workload, Nginx. And in this situation, it's using about 12 of the cores in the system. And we've got these spare cores that aren't doing anything. So then what we did is we took sort of this, we call it an aggressor workload, MLC. It's a sort of a stress test that we have internal. And we drop that down on 7 of the cores. And when we do that, this thing is really stressing the memory bandwidth of the system. The performance of Nginx drops by 23%. That's bad. This is exactly what we're trying to avoid. And so what we can do with MBA is we can come in and we can actually control what's actually happening in the system when we detect this problem. We can recover the performance on Nginx, get it back up to about 0.98, and still be able to take advantage of those spare cycles as they're available. And so that's kind of the idea of the things that we're trying to build here.
So how does it affect like the PCIe bus? Is there some monitoring and control over access to that bus?
We don't have any direct control over the PCIe bus today. You can measure like the memory bandwidth that's coming in from the PCIe bus or the total aggregate memory bandwidth in the system. So if, for example, you had a large amount of traffic coming in from PCIe, you could detect that that's happening and then decide if you wanted to throttle the cores back in response to that in order to sort of manage.
At the memory level.
Yeah, but today the way that we would do that is you would sort of look to the cores and figure out which of the cores you would want to throttle back in order to control that aggregate system bandwidth.
So is that something that might change in the future?
We're always looking for opportunities to do further QoS optimizations, so yeah. OK, So the next set of features that we have in this generation is something that we call speed select technology. In this gen, we actually have 3 new types of features for speed select technology. So the first one is what we call speed select core power. So what this feature is trying to do is you can imagine you can put some high priority workloads on a subset of the cores. And then if you're running with turbo and you run out of power, and so normally what we would do is we'd throttle all the cores down. Instead, what we can do here is we can say, all right, for this pile of cores here, I don't really want you to throttle them. And so then they can stay up at that max all core turbo frequency while we use the other cores as kind of like a relief valve, and we'll throttle them down. So you can kind of see that here in this picture here, where so what we have here is this is sort of time. And then on this axis, we have the frequency that we're running at. And so traditionally, if we ran out of power, we would throttle all the cores together. And then here what we did is we took half the cores and said, you're high priority, and half of the cores, you're low priority. And that then allows us to sort of separate out which frequency those different cores get at. And this kind of gives you the ability to sort of steer how we throttle the performance or the frequency of the system when we have a power-constrained environment.
Does it require manual intervention, or is it an automated process?
So you would specify ahead of time, these are the cores that are important, and these are the cores that are less important. And then it's all just automatic.
Do they have to be lumped into a certain number of groups?
No,
Like,
you just say this guy's high, this guy's not.
And is that a boot time decision, or is it?
Nope. All of our time.
so it could change on the fly.
Absolutely. On a per core basis, yeah. So speed select based frequency is kind of similar. This one's actually is a boot time decision. But what this allows us to do is sort of traditionally you would have a single P1 frequency or base frequency across the system. And what we heard from some of our networking customers is sometimes they have like a small set of work that's really important, and they really want to bump that guy up and have consistent performance across a subset of the cores. And so, we can build that for you. You care about something predictable. You want to know what the frequency is, and so we went in and I built these networking SKUs that actually had elevated P1 frequencies for a subset of the cores, and that then would enable the customers to sort of put their really high priority workloads onto those cores and have guaranteed performance like they would normally get out of a P1 frequency with turbo disabled. You can combine these technologies if you want. That all works just fine. But again, this guide today is a boot time decision. The last one that we have is sort of is speed select technology power profile. The way I like to think about this one is it's like 3 SKUs in one. And so we had a lot of customers that were like, I've got to buy this high frequency SKU from you. I got to buy this high core count SKU from you. Sometimes I really don't know how many I'm going to need. That need may change over time. How can you guys help me out here and just sell me one thing and I'll decide how to use it? I said, all right, we can do that. And so what we've done is we've sort of looked through and looked at all the different types of components that are there in a SKU design, TDP, TJ, frequencies, core counts. And we can build SKUs that have 3 of those, and then the customers at boot can decide what mode they want. So then what we've done is we've gone and actually helped develop the open source ecosystem so that they can actually manage this through open source tools and say, all right, I'm going to need an instance and I want it to have 8 cores active. They go set it up, reboot the system, and bam, they get an instance with 8 cores active. So that's sort of the idea here, is really giving our customers flexibility with the solutions that they're buying so that they really can simplify their infrastructure and they can have more flexibility with their infrastructure depending on the needs that they have at a given point in time.
It's QoS for the processor.
Yeah, it's QoS for the frequency and the cores and exactly. QoS, flexibility, those are kind of some of the main things that our customers are looking for that we're trying to bring.
Interesting.
How different is that from say the consumer side with Intel SpeedStep? Pretty similar?
So Turbo 3.0 on the consumer side, they're kind of focused on I have 1 or 2 cores active, and I want to get crazy high frequency on those cores because I've got a lot of consumer workloads that just want 1 or 2 cores for a non-trivial amount of time. If we go talk to our server guys and we're like, how often do you run with 1 core active? They're like, hopefully never.
Yeah.
Right.
I've got 28 cores.
Yeah, I want to use all of them.
I want to use all of them, please. So, we looked at that. We're like, all right, that's not working. But if 8 cores active, maybe that's something where you can try to take advantage of it. So it's It's kind of similar in concept. It's a very different implementation, very different
Much bigger scale.
physics and constraints behind the board of like what actually drove those things. But the same kind of conversations of what are your workloads really doing? How can we kind of manage power and performance within the system and really help you optimize your infrastructure? Okay, so last topic. I'm only going to go a little bit long, I think. So hardware security mitigations. So we've talked about this a good amount. I think a lot of people are aware that we're putting a lot of hardware mitigations into Cascade Lake today, into this second-gen Intel Scalable processor. And so I wanted to tell a little bit of a story here about like what's actually happening inside of Intel, how are we actually approaching this problem. So early on, we had variant 1 and 2, as well as variant 3. And so we're like, all right, we gotta figure out how to put some hardware mitigations in. But what we don't want to do is just sort of like come up with a point solution that just fixes a specific problem. So we're trying to look for general ways that we can implement hardware mitigations for these types of problems. And so one of the ones that we added for variant 3 is what we call hardware hardening for memory faulting. So if you guys are familiar with it, one of those attacks, what they're doing is they're trying to look at load operations that would normally cause a fault in the system and then taking advantage of a side channel created there. And so we put a fix in for that, a general fix, not a point solution. And then later on, L1 terminal fault was discovered, not by Intel, by an outside researcher. We didn't know anything about it when we put the hardware fix in. We didn't have to change anything. It was already mitigated for us by the fix that we had put in for variant 3. That's a lot of the things that we're trying to do right now is just continue to look at places that we can really harden our system so that as new discoveries get made, if new good discoveries get made, we've got good general solutions that have hardened parts of the architecture and make it less likely to be attacked. Okay, yeah, question?
So for some of those, especially the ones that seem to be more appropriate to hypervisors, do those hypervisor manufacturers have to make code changes in order to use these features?
For the most part, no. So like, there's some change here to enable IBRS, but it's like, stop doing what you were doing before with IBRS and instead turn on this bit. And so it's a change, but it's not a lot. Other things, like some of these changes down here, the OS or VMM is involved in some of the management of the system, and that's something that would happen more dynamically. So it kind of depends. And that's kind of the way we're looking at this is, which of these things do we want to just sort of set and forget? Which of these things that are better solved between software and hardware together? How do we sort of solve this as a community as opposed to, just like, narrowing our view and trying to solve it that way? So that's sort of our approach. Okay. All right, so a little bit on performance. So apologies, this slide's a little bit tough to read. So the first batch of benchmarks that we have here, we've got gray, which is sort of what we would have had as our baseline with a mitigated Skylake. And then the blue is sort of what we get after we move to Cascade Lake, to the second-gen processor. So the marketing guys made me put in all of the performance gains with turbo and everything else because they didn't want to have flat lines across the scaling of generations. So if you really just did sort of an apples-to-apples comparison of, with mitigations on Skylake and with the hardware mitigations on Cascade Lake, all of these would just be a nice boring 1.0. They didn't lose performance in the past. It doesn't matter if we have mitigations in the future. They don't care. Now, some workloads like FIO, depending on how you used FIO on a mitigated Skylake system, it could actually see some pretty big performance losses. It's kind of like one of our classic benchmarks that kind of show where the mitigations that we put in can actually see a non-trivial performance loss. And you can see with the hardware mitigations that we put into Cascade Lake that we get a 38% improvement on that workload because of the new hardware mitigations that we've made. So where's the reality on real workloads? It really matters on different workloads. So we're looking forward to our different customers testing their real world workloads and seeing what they observe.